So, welcome everyone to the 19th lecture on statistical theory for deep learning. We started in the last lecture to combine our results for neural network approximation and neural network generalization in order to derive bounds on the expected error of neural network least squares, neural network regression estimates. And as a preliminary result, I formulated and started to prove theorem 4.1. You have bounded random variables x, y, x1, y1, and so on, which are IID. X takes on values, no, it's here unbounded, x is in values in RD, but y is bounded. The value is in some interval from minus beta to beta. I want to estimate the corresponding regression function m of x, which is the conditional expectation of y given capital X equal to small x. I use the least square estimate, so I have fn a set of functions from Rd to R. Later on this will be sets of deep neural networks. We minimize the empirical L2 risk over the function space fn, so I choose some function m and twiddle depending on my data x1, y1 up to x and yn, such that m and twiddle minimize the empirical L2 risk 1 over n, sum I equal 1 to n, f of xi minus yi squared. And I truncate this estimate, so that mn of x is equal to t beta mn twiddle of x, where t beta is a truncation operator which truncates the real number beta in the interval from minus beta to beta. So if it's already within this interval from minus beta to beta, you just keep the number as it is. If it's larger than beta, you replace it by beta. If it's less than minus beta, you replace it by minus beta. Then I look at the expected L2 error of my estimate. So the expectation of the integral of mn of x minus m of x squared integrated with respect to the distribution of x. And I want to show it's less than or equal to a sum of two terms. The first term is a constant times beta with exponent 4, which is another constant, times 1 plus a supremum over log of L1 covering numbers of the truncated function space t beta and fn with radius 1 divided by at beta times n on points x1, n, and then take a supremum over all possible choice of these points, plus 2 times an approximation error, which describes how well the best function in this function space can approximate the regression function in the sense of the with respect to the L2 error. So it's the infimum over f and fn integral of f of x minus m of x squared integrated with respect to the x. And we have seen already from this proof, and by the way, this proof will be on the list of exam questions, and the error decomposition which is used here will be given as a hint. We have seen that already from proof that if we use the following error composition, we rewrite the expected or the L2 error of our estimate as which is equal to the L2 risk of the estimate. And since this estimate depends on the data dn consists of the random variables x1, y1 up to x and yn, I have to compute here the conditional expectation of mn of x minus y squared given this random variable, minus the L2 risk of the regression function, minus expectation of f of x minus y squared, and then I subtract one term and add one term, so I make nothing, and what I subtract is twice times, subtracting track is twice times an empirical version of this L2 risk of the estimate minus the L2 risk of the regression function, which is the empirical L2 risk of the estimate minus the empirical L2 risk of the regression function. So I subtract twice, 1 over n times sum I equal 1 to n mn of xi minus yi squared, minus 1 over n I equal 1 to n m of xi minus yi squared, plus twice this time. And then the first two lines together is my first term, t1n, the second is my second term. We have already seen the second one, I can upper bound it by replacing mn by mn twiddle, because my yi's are in the interval from minus beta, and therefore the truncation brings this estimate closer to the yi's. And if you have the have an equivalent, then you can replace by the infimum over all f and fn of the empirical algebras, then you compute the expectation. The expectation of the infimum is less than the infimum of the expectation, and then the whole thing is just 2 times the infimum over the true error. So you get your second term. So it remains to show that the expectation of T1n is less than this first term on the right-hand side of the theorem, and that's what we are doing next. Questions so far? Then let's start with the first term. And how to do this? Well, it's so it's proof of theorem 4.1, continuation. We have. Well, I have to bound this expectation of T1n. And what I want to do, I want to use our previous results from the beginning of chapter 3, where we had a bound on the difference between expectation and sample averages uniformly over function spaces. And I use the second theorem, the Lee-Bartlett-Williamson theorem here. And this gives something on the J probabilities, so the probabilities that these terms are greater than some t. I have to reduce this to the J probabilities. So I basically want to bound the probability that T1n is greater than some t and want to relate it with the expectation. And first, I could use now from probability theory, the formula you know for how the expected value can be expressed by integrals of the distribution function. And there's one easy formula which we have done in the lecture, which was for non-negative, or this, the basic function, the basic relation is for non-negative random variables, and there's one more involved, which you had in the exercise of the practicing course about the whole thing. I could use this more involved. Instead, I use the easy one, and for this I make the following trick. I upper bound to get a non-negative random variable. I just replace the T1n by the maximum of T1n and 0. And then, of course, the T1n is less equal than the maximum of T1n of 0. And first thing, so I have this upper bound, and second point, now I have a non-negative random variable, so I know exactly what how to express the expectation with tail probabilities. This is just the integral over 0 to infinity of probability of the maximum being greater than t. And now I can forget about the maximum of T1 and 0, because if the maximum of T1 and 0 is greater than some number t, which is greater than or equal to 0, then this T1n must be greater to 0. So I just get this one. And now I want to bound this one. Okay, you don't see it at the moment, but I make another trick here. I will use another bound, and of course this probability will be, it's a probability, so it's always less than 1. So I can also replace it by 1. But if t is very close to 0, then this will be, my upper bound will be greater than 1, so I don't make this one. So I choose for any delta n. I make delta n greater 0, and actually I use delta n greater than 1 over n. You don't see at the moment why I use delta n equal 1 over n, but it's at the moment I just use that it's greater than 0. So we make split integral up from 0 to delta 1 n 1 dt And then from greater n to infinity, I plug in my probability. Then you see, of course, that's the first one is delta n, and the second one is this integral. And I do this because I know that I can upper bound this probability, which you don't see at the moment. So if you have t greater or equal than delta n, or delta n was greater or equal than 1 to n, I look at this probability. And you just plug in what it is, yeah? And that's this round formula. So you plug in this guy here, and I don't want to write it, but I can use next, I have a problem, because I have well, basically it's a simple quantity, it's an expectation minus twice the sample average, but unfortunately it's a random expectation, because my function here is random. I get rid of this randomness by using that this function is a truncated function from my function space Fn. So I can say if this one is greater than t, then there must exist some function in the truncated function space which satisfies this equality. So I'll make an upper bound. Exist f in t beta, introduce it as t beta, right? Yeah. And it's a probability, sorry. And then I have now I can replace the conditional expectation by the expectation with f. That's expectation of f of x minus y squared minus the 2 of the regression function minus twice the sample average of it. And that should be greater than t. So here I use that that's one function of my truncated function space by definition. And now you have to remember what we did before. And I have the old slide here. Was not without glasses. Should be 19, it should be. That's obviously the wrong one. I have it here. And no, it was May 29. Choose this. Yeah, got it. That was the theorem we have proven. It was theorem 3.2, and I want to apply this one with f replaced by t beta n, fn. And then you see what I have here is the L2 risk of the function minus the L2 risk of the regression function minus its empirical version, corresponding sample average, greater than some epsilon times alpha plus beta plus L2 risk of the function minus L2 risk of the regression function, which is not what I have here again. Here I have L2 risk of the function minus L2 risk of the regression function minus twice its empirical version greater than t. But the trick is now I add to both sides this term once more. Then I have 2 times this difference of the L2 risk minus the empirical L2 risk greater than t plus something, and then I divide it by 2. So that's the same as the probability that I have n. I write the expectation of x minus y squared minus expectation of m of x minus y squared minus the sample average once. So you see, if I add 1 times this difference of expectation to the left-hand side, then I have this by a factor 2, so I divide it by 2. Therefore I get greater than 1/2. Then I have a t, I write t as t half plus t half. And then I get this expectation difference on the right-hand side. And I got this part. Okay. So this was a trivial reformulation of our right-hand side, and now I match it with this theory. You see it has exactly this form. Exists f in f, calligraphic f. You have to replace the calligraphic f by the t beta and fn. You have to see what is epsilon, what is alpha and beta, but it's basically opposite of this, yeah? Epsilon is 1/2, alpha is t half, beta is t half. And then I can apply directly the bound. To conclude, so we apply theorem 3.2. And we get this 14 times the supremum over x1n. You have an L1 covering number. Now you have beta times epsilon divided by 20b. Beta was t half. T was greater than 1 over n, and I replaced directly in the covering radius of the covering number my beta by another bound, and then this covering number gets even larger. So instead of beta and instead of t half, I write n half. No, I write 1 over 2 times n. That's my t half. Then epsilon is 1/2. Then I have a 20. Then we think about what is my b. My b was the bound on my functions f and on my y. And here you see in our previous theorem, our b, you don't see it anymore, but our b was just a beta. So that's better. times f n. Then we have e power minus is epsilon squared times 1 minus epsilon. Epsilon squared is epsilon was 1/2. So it's 1/2 squared times 1/2. Alpha was t half times n times 214. 1 plus 1/2. It's 3/2 times beta with power 4. So I need this guy. And now you just write this a little bit nicer. The first one is 1 divided by it's 2 times 2 times 20, that's 80 beta n. Oh, and there was a mistake here. It's not f. It's t better than fn. And the other guy is e to the power well, it's t times n in the nominator, so n times t, and the denominator gets in factor well 4 times 2 times 2, that's 16. Here you divide by this 2, that's 8. 8 times 114. I don't calculate this. No, 20, and I've forgotten this 24 times 214, because I have forgotten this factor 3 here. Times this exponent 4. That should be correct. Now you plug this in your bound. So we have this bound, plug our bound with a J probability in this integral. So the expectation of T1n is equal delta n plus this whole integral from delta n to infinity, and you plug in this term. Then you integrate, you see how you can integrate this guy. You use as a, for the fundamental theorem of calculus, you use the function which gives as a derivative this function. I multiply this function by minus this guy divided by n. And then I evaluate it at plus infinity and minus infinity. Plus infinity gives you 0, so I just have evaluated minus infinity. I get using minus, so I can forget about the minus. So I get 14 times of x1n, and 1 divided by 80 times n. I get from the derivative, I get the beta with exponent 4 divided by times 24 times 214 divided by n times e with power minus n times delta n. 24 times 2 into 14 times exponential. So yeah, this guys. Okay? And I did several things at once, but I think that's easier. Question?
On the lower board in the second line, the lower board?
The lower board in the second line?
Die untere Tafel.
Okay.
Links?
Yes?
Yeah, that in the second line there should be an inequality, right?
There should be an inequality. This is an upper bound, yeah? You're right. Thank you. My mistake. Any more writing errors? So now you see you have this upper bound for each delta n. Now you minimize it with respect to delta n. And what you basically do, you choose delta n such that this term times this guy, so this supremum, times this exponential value is 1. And if this is the case, then this one is a 1 over n, or constant over n. And then the delta n basically will determine what the upper bound is. And if you do this, what do you have to do if you want to get this term equal to 1? Well, the whole thing here should be the log of this supremum of the covering number. If this guy gets the log of the supremum of the covering number, and then you see how can I choose delta and such this time, because if this time gets the log of the supremum of the covering number, then e to the power minus thing is 1 over the supremum of the covering number. This cancels out. So we do it in this way. What do you have to do? This should be 1. So I first add this full factor in front. 24 times 14 times 24 divided by n. And then I make the log of the supremum of the covering number, and it doesn't matter whether I make a log of the supremum or the supremum of the log. I should make the supremum of the log. Log of the covering number. 1 over 80 beta n. So there's this guy. If you plug this in, then the whole second term on the right hand side gets something constant divided by n. And the whole first term on the right hand side is the delta n. If you look at the delta n, now I have to go back to my assertion. This would make sense. Let me go back to my assertion quickly. Maybe it was here. Yes. Then you see we get exactly the supremum over the n times some constant. Because that's the form of the delta n. So with this we get the assertion. Questions? So you see this delta n is a constant times this of log factor divided by n. And the 1 over n constant times beta 4 times 1 over n comes from So this guy here, yeah? Because this whole thing is one. Questions? You want to mention it? Yeah, okay.
So on the slide there it says 1 plus is prima.
Yes.
I don't see it.
You don't see the 1 plus, well, you have here a sum of 2 terms, yeah?
Ah.
The first, get this without the 1. It is 1. But the second one, there here, this guy is what the one which the equivalent below is 1. So that's the constant times beta 4 divided by n. And you need this 1 plus because it might be that this covering number, or this covering number is, in the extreme case, could be 1, and then the log of it would be 0. Can't be. Okay, any more questions? Then I can stop this quickly here. I need to make one comment. It's a remark. Well, in the theorem I assume that my y are bounded and you can actually relax this. And this was done in the seminar, in the first seminar talk. I won't make it here. It can be shown that the assertion of theorem students if this assumption is replaced by where you need an exponential moment of y squared, so you need it e times y squared, so that's an infinity, and you need an addition that the regression function is bounded. And then you replace beta by something which goes slowly to infinity, and you can prove the same theorem. Why is this important? I will next use theorem 4.1 to derive a rate of conversion for least squares neural network regression estimate, and then we will talk about the optimality of this upper bound, but for this I have to prove a lower bound, but the lower bound requires unbounded distribution. In additional, in particular, it requires y to be normally distributed, and for normal distributed, such a thing holds. E with exponent constant times y squared is less than infinity. This actually is called the sub-Gaussian condition for some constancy, depending the constancy will depend on the variance. Okay, any questions up to that point? Okay, then I make a break, 5 minutes for cleaning the blackboard. It's now 10:24, so it will go on 10:29. So I would like to go on. What we do next, we apply our previous theorem to special spaces of neural network. And here, in order to bound the approximation error, we need some smoothness assumption on the regression function. We will assume, as we did in chapter 2, that the regression function is PC smooth. So it gives section 4.2, rate of conversion of least squares neural network estimates. Then the question is, what kind of neural networks do we consider, or space of neural networks? Well, we do use these neural networks which we have used in chapter 2 to approximate our smooth function. So we use it with ReLU activation function. Sigma of x is the maximum of x in 0. We consider spaces F, or I introduce again the notation FLR for the space of neural network with L layers and R neurons per layer. And R be the corresponding of neural networks. And these define some function, and I define this function in RE. With capital L layers. And R neurons per layer. And then, if you remember what we did in chapter 2 about neural network approximation, I used neural network or real neural network to approximate local convex combination of Taylor polynomials, and for this we use the sum of such function FLR. This gives me the space Gn. Is the set of all functions. Well, these are actually sums. I use S equal 1 to some number of functions which will depend on the sample size, Kn, and it's some function Fs. Where Fs is my function space, and again, the number of layers and the number of neurons will depend on the sample size. For S equal 1 to 3. 1 to 3. And again for some we have parameters Kn, Ln, Rn. And then I've defined my estimate as before, truncated least squares estimate. So I have a truncation operator that beta n. It's just the corresponding least squares estimate. So it's the function of my function space called G. which minimize the yield to this one, and then we truncate it. So our Mn is our truncated least squares estimate corresponding to our function space G. And what I will now formulate is a theorem where I bound the expected L2 error of this estimate in case that the regression function is PC smooth and x is bounded. And I use here some interval from -a to a is power d. And y is again bounded, then I use beta and as is bound. And then we choose kn, ln, rn suitable that we get a nice bound. So of course we use the previous theorem, so you can see you get an error bound by two terms. One is the log of the covering number divided by n. The other one is the approximation error. And of course the k and ln, rn will influence simultaneously the covering number and the approximation error, but in opposite ways. As larger this k and ln, rn is, as better will be the approximation error, but worse the approximation bound. So basically you have to balance them. And this leads to the following theorem 4.2. We have PC smooth functions, so I have PC greater 0, and also I need bounds on my random variables. I use a capital A and a beta. PC beta to 0. I let x, y, x1, y1, and so on be IID minus AA, random variables with values in minus AA with x1 d times minus beta beta. D, and what the values I take on is minus in D times minus beta beta. And I assume that the corresponding regression function is PC smooth. X, conditional expectation of y given x is PC smooth. And for simplicity, I just assume that you can find a version of this conditional expectation which is defined on whole RD that is on whole RD PC smooth. Because I think whether it's sufficient to assume that it's just on the compact interval PC smooth, but I don't know at the moment. Now I choose OK. For beta, and of course I set equal to beta. And now the parameters which you need is kn, ln, rn. And these you choose from your approximation result. And if you remember our approximation result, well, the ln will be just some log of n, some log term, and the rn can be constant. And the kn is the main bound on the approximation error. And it turns out for kn, the right thing to do is kn is upper Gauss bracket constant 1 times n with exponent d over 2p plus d. You don't see this at the moment. So I could start with a general Kn, I could start with, but I could start with ln. Ln is clear. Ln is a constant times with n, and Rn is a constant. So you could start with this value of ln, Rn, and Kn, and then I derive depending on Kn upper bound, and then I minimize this upper bound as a function of Kn, and this will come out. Don't do this at the moment. And then the question, then the assertion is in the C1, C2, C3 sufficiently large. Or expected L2 error. Is less equal than some constant C4 times some log factor, this log n with exponent 4 times n with exponent minus 2p over 2p plus p. That's our bound. So you see, as smoother the function is, as faster this bound goes to 0. You see, as larger the dimension is, as slower this bound goes to 0. And we will see in the next two lectures then that this log factor is, that this bound is optimal under this log factor, and actually one can prove that the optimal rate would be without the log factor, but that's not a problem. The point here, because such a bound I can prove easily for other estimates, but the main point will be in the final section of this chapter, that we show that we can do something about this dependency on D here. Because this dependency on D is worse. That's really a bad thing, because usually your regression problems in applications are large. You have a large information vector which you use to predict, and then you get here very slow weights. And due to the fact that this bound will turn out to be more or less optimal, you cannot do anything about this, but impose further assumptions to get rid of this or get better bounds here, and there's a nice way to do this for neural networks that you will see in the final lecture, or one of my last lectures. Okay, that's our theorem, and I guess you see immediately how to prove it, yeah? We apply the previous theorem. What questions so far? Any questions? So by theorem, that was 4.1. No. Our expected L2 error. Is less equal. First constant, and I have used already C1, C2, C3, and C4, so I call it now C5, times 1 plus the supremum over all x1n of the logarithms of the L1 covering number. Anyone remember this radius? It was something like 1 divided by 80 beta n. Yes. 1 divided by 80 times n times my truncated function space x1n divided by n plus the second constant times the approximation error. No, this was basically the 2 here, yeah. 2 times the approximation error g and the integral of g of x minus n of x squared dx. And now you see what you have to do. You have to bound this covering number, and you have to bound this approximation. And we had all the theorems we need. We had one theorem which bounds the covering number with the, well, the covering number was always less than the packing number. We had some general theorem about packing numbers involving the VC dimension of subgraphs. You have here VC dimensions of truncated functions. You easily see that this VC dimension of the truncated functions is less than the VC dimension of the function itself. Because if such a truncated, if this t beta and gn, beta gn, if this shatters some points, x1, y1, and yn, and the VC dimension was the maximal number of points which can be shattered. So shatter means that you can look at the subgraphs, you look at function sets of the form xy, where some function g from a function space g of x is less than y. And then these functions must be able to pick out each subset of this. If they can pick out each subset, well, these functions are bounded by these functions take on value in minus beta beta. So if here one of the values is either larger than beta or less than minus beta, then it will be never in such a can be picked out by such functions here. So then it cannot be shattered here. When ye less equal beta, I equal 1 to n must hold. But then if you intersect the point, or look whether a point is in the subgraph, it doesn't matter whether this function is truncated or not. Must hold. Therefore, Gn shatters. Which implies the VC dimension of the shattered functions, subgraphs, is less than the VC dimension of the function itself. First part. Second part, I would like to give a bound on the VC dimension of Gn. Any idea how to do this? How can we get a bound on the VC dimension of our sets of neural networks? Which theory was it?
Bartlett.
It was the Bartlett theorem, the second Bartlett theorem, Bartlett et al. I think it was 3.6, something like this, yeah. And it gives which bound? So by theorem 3.6, you know this VC dimension, there's a plus here, sorry. The bound depends on what?
The layers and the amount of weights in the.
The layers and the amount of weights, so the number of weights and the layers. So the ln is 1, and the number of weights, how many weights do we have in here? Well, or other question, what is the depth here? We need two things, the depth and the number of weights. What's the depth in this? Special space of neural networks? Well, how does it look at all there? Well, it's a sum of neural networks, yeah? So you can say these are kn many in parallel computed neural networks. And then this sum is just the output of it, yeah? This doesn't increase the layers here. The layer is in here, and if you look how much is the layer here, there you see it's ln, yeah? So the number of layers, the depth is ln. That's easy. But what's the number of weights? And we don't need it exactly, we need it only up to some constant. So the GN has ln layers and constant many weights.
So in every layer there are Rn square many weights?
They are Rn squared, or Rn times Rn plus 1, but it's roughly Rn squared, and then you have 1 with Rn times d plus 1, so, but it's a constant times Rn squared, yeah? In every layer, and you have
times the amount of layers, of course.
ln times Rn squared would be, correct?
We have kn many.
But we have kn of them. So you have kn times ln times Rn squared. We have these many weights. And then we need which? We get what kind of bound for the VC dimension? Do you remember?
I mean, if I got the right one, then it's constant times the number of layers times number of weights times log of the number of weights.
Yes, you have the right one. So it's constant times the number of layers times the number of weights times the log of the number of weights. Yeah. So we get here what kind of constant? I have now is 6 times then the number of layers is ln. Then the number of weights, I can forget about this constant. It's kn times ln times an squared. And then the log of kn times ln times n squared. And now you look at how we defined ln, kn, rn, yeah?
The theorem used was 3.7 in the lecture.
The theory was 3.7, thank you very much. And the 3.6 was the Hausler bound, or the, which I don't call Hausler, but we actually need next. So, if you look now, what is this? Well, okay, this is a log n, this is a log n, this is a constant, so you have your log n squared. The kn is the big one, the kn is of order n to the power d to 2p plus d. And if you multiply these whole things out, then well, that's bounded by some polynomial, because that's n to the something times log times const, and the log is just a log n. Yeah? So we have here some additional log n, log n, log n, log n, it gives log n to the power 3. So we have c7 times log n to the power 3 times n exponent d over 2p plus d. And I can forget about the Gauss bracket. This guy. Now we want to use it to bound the covering number. In order to do this, we use our bound, which gives a bound on the packing number by some function of the DC dimension. And that was theory 3.6. And I think we had a previous lemma. Was it lemma 3.1 or what? I don't know. But we've basically basic theory is 3.6. If you look at this covering number, 1 over 80 times n t beta g n x1 n. You bound it by the packing number. Maybe I should use, I have it here, left, right, sync. So actually I have the right slide here. Got it. We got this part, yeah? It was theorem. Okay, it was 3.5. Sorry for that. So you see the whole thing is less equal 3 times 3b. Well, you have here functions from 0 to b, but we apply it to functions from minus, with values in minus b to b, minus beta to beta. What you do, you shift all functions by some beta, then you get functions with value from 0 to 2 beta, and you easily see that the shifted functions have the same packing number as the not shifted functions. So my b is 2 beta, so I have 2e times 2 beta, divided by epsilon. Epsilon, you see, is 1 divided by 80 beta times n, times the log of the 3 times e times 2 beta divided by 1 divided by 80 beta n. And now I plug in the VC dimension of the subgraphs. And then you plug in everything together and get your bound. Maybe we can do this at once. If you look now at this 1 plus the supremum, or basically I can forget about the 1, because that just gives you 1 over n. You can ignore. And look at the supremum over x1n of the log n1 divided by 80 beta n times little gn x1n divided by n. Any idea what you get? We plug in now all of the terms which we have together. We have this bound, we have this bound, we have this bound. And you make the log. Well, this looks a little bit ugly because it's a term times log of the term, but you easily see this term is much bigger than the log of the term. So you can forget about the logarithms and maybe just make a factor 2, but constant here in the BC dimension, but constant factor doesn't matter. Right? So it's basically this term, if you look at this term, this is basically n, constant times n, this exponent. Then what is the logarithm of this? You have a constant times n with exponent of the BC dimension, you take the logarithm of it divided by n. What's the right part? Any ideas?
Maybe have something like C dimension times the logarithm of this inner part.
You have 3c dimension times the logarithm of the inner part, and this inner part is basically constant times n. So you see it's or constant times n or something like this. So the inner part is basically log n here. Or the log of the inner part is basically log n here. So you get something like log n times 3c dimension.
I think we take like constant, and then the thing at the bottom is log n to the power 3. We get another log n, so it's log n to the power 4.
It's right, so I have now a constant 8. I get the log n to the power 4. I have it bound on the BC dimension without the log n and without the constant. So it's n to the power d divided by 2p plus d divided by n. And that's it. And now you see what this whole thing is. That's constant 8 times log n with the power 4 times n. It's with exponent d over 2p plus d minus 1. So it's d minus 2p minus d divided by 2p plus d. That's minus 2p divided by 2p plus d. That's the right thing. And that was the bound we wanted to get. You don't see it here, but that was the right bound which we want to get for both terms. So the first term is fine. Now we need something on the approximation property of our spaces, and we had some results in chapter 2, and it was theorem 2.1. And let me look for the corresponding slide. Was from May 15. We have theorem 2.5. and by May 15, and by theorem 2.1. What we had is this, we have this infimum. Gn, integral of g of x minus n of x squared dx dx. This I want to bound. I have to bound under two arrow with respect to some probability measure. My probability measure has support, which is or takes some values in the interval minus AA with power exponent d. So you can bound this one by the subnorm with respect to this interval on this interval minus AA with power d, and the subnorm squared, yeah, that's squared. Then you have this infimum over the g and gn of the subnorm squared, and that was just our notation d, g, d regression function, gn, and the subnorm. So that's less equal than, here I use x in minus almost surely. I got the squared of d, it's my regression function. I have m, we have our function space Gn, I have the subnorm, my interval, the whole thing squared. And now you have to, you see, if you define the function space in this way, then you get this bound constant divided by 1 divided with, of k with exponent p. And now you have to look what is your k, how is this related to the kn in our function space and the kn in the function space. I think it's hidden somewhere behind. Let me see whether we can do it. Not really. But maybe if I make it a little bit up. More like here, and then if I turn this on temporarily, then you see what our Gn is, yeah? That was our Gn. It's a linear combination of Kn of this function from f, l, and Rn. If you compare now with what we had here, we have a linear combination of k plus 1 with exponent d times this number of terms of these guys. We have our depth is something like p plus d times log of this k times log of a constant, and the width is a constant. Width is fine. If you look at the depth in our theorem, the depth is that's written here. The depth is constant times log n, but the k will be something like polynomial, so that's log n2. So maybe the depth might be a little bit too large, but that's not a problem with the ReLU networks, because you always can have this FID network, sigma of x minus sigma of minus x is x, so you can get the depth arbitrarily large. So the depth should be okay, the width should be okay, and now just the question is what's the relation between the kn here and the k on the slide. And then you see what I have to insert here is constant. Maybe we make it C9 times squared of 1 over my k with exponent p. But you have to tell me what the relation between kn and k is here. Any idea? Well, of course, I could just plug in here kn is exponent p. What about that? Maybe I should see again the definition of G. Any idea? Well, maybe you forget in this function space G there's a double sum. Maybe forget first for the inner sum. Because this is sum over a constant number of terms. It will be at most p plus 1 with exponent d, something like this. This is a constant, doesn't matter. Yeah? Then what is the relation? How if we choose k such that k plus 1 with exponent d is equal to the kn? So I have k in terms, and instead I want to use the sum over k plus 1 with exponent d. Yeah?
Dth root of kn and minus 1.
Dth root of kn minus 1, yeah? And we forgot about minus 1 because we are not interested in constant. So it's the dth root of kn. So we get instead, and here we have an additional constant, but additional constant doesn't matter, yeah? Because it's just a constant here. So what we get from the size is not a kn with exponent b, but kn with exponent b divided by b. That's what we get here. And now if you plug in what kn was, how kn was chosen, how kn was chosen, then you will see you have a kn with exponent p divided by d is basically an n with exponent p divided by 2p plus d. You have it in the denominator, you square it, you get the c10 times n with exponent minus 2p over 2p plus d. And let's finish the proof, because now we have both terms have the right order. Any questions? And now you also see why I have chosen Kn in this way, because you see this was basically Kn here. So you have to balance Kn divided by n, and Kn 1 divided by Kn is exponent 2b divided by d. And if you balance these two guys, then you end up exactly with my choice of Kn, which is constant times n is exponent d over 2b plus d. Also you see that this Kn has different influence. Here the term will be larger, as larger Kn is, and here the term will be smaller. So you basically choose it such that both get the same. And as in the previous theory, we have the following remark. This theory also holds if you replace the assumption that also holds if assumption y is less equal beta almost surely is replaced by the expectation of e with power. Now I need a new, maybe I make some C1 bar. And the signal of n. Which is boundary. And this just follows from the previous remark, because you apply just theorem 4.1 with the previous remark, and you get the same bound. And then you see it holds in particularly if y is normally distributed and the regression function is bounded. And in this special case, we will also derive a lower bound in the next, I think, 1.5 or 2 lectures. Because next question is, okay, you have some rate, but is this somehow good here? Or of course, it could be I can improve my proof to get a better bound, or I can improve my estimate, choose another function space to get a better bound. Yeah? And it turns out, no, you cannot improve much up to this log factor, and this log factor, well, that's some problem because these neural network function space are rather large. I can do it even in case of neural networks if I make a least square estimate where I choose this function in a special way. I choose the inner one. I don't allow all weights. I just restrict the weights. I just use the weights which we needed for the good approximation results. And then I have a linear least squares estimate, and for linear least squares estimate, I can get a nicer bound on the covering number with a different proof and get nicer results. But that's not the point here. I'm not talking about log factors. We are talking in general of the rate. We will see the rate has this right size, but then this rate is bad because of the d here, and we will see the neural network enables us to impose some nice condition to get some better rate. Okay, any questions? Then I'm done for today, and see you on Monday. Thank you.